when you read this particular problem about smokers and their heart rates, tell me why this is not matched. Two totally different populations. Why could it not be a matched situation? Perfect. Okay, you can't be a smoker and a non-smoker at the same time. Doesn't make sense. You have to have two totally independent situations here. So this is going to be a two-sample t-test. We know that in our state step that we got to name the test, and so we'll go ahead and do that. It's a two-sample t-test. Why is it a t-test and not a z, by the way? Because we're with means. When is the only time, and it's rare, we haven't really done one, but I've at least mentioned it several times. When's the only time with means that you'll use z procedures? Of what? Both population standard deviations, right? Which is so unusual and so rare that we just don't really ever do it. We just mention that it could exist. Okay, so two-sample t-test. We probably also need to talk about our two different populations, right? And so what are our two different populations? Smokers and non-smokers. So since they talk about smokers first, I tend to call that going to be, I'm going to call our two different proportions. So mu1, think about notation. With proportions, you should have been talking about your parameter of interest in terms of p, because it's a proportion. But with means, we're talking about mu. So we're going to say that this is going to be the average heart rate of smokers. Maybe you can throw the word true in there if you want to. That would be good. And then mu2 would be my second parameter of interest, because we're comparing the two different populations, and that's going to be the average heart rate of non-smokers. Important to define those, because when we talk about our ho and our ha, we want to just be able to use the notation. We don't have to write it in words as long as we talked about a parameter of interest and defined what they are. So just like with proportions, when you have two proportions, how can we write our null hypothesis here? Mu1. Okay, so this is one way to do it. I tend to not do this, but this is totally okay. The difference is 0. I tend to say mu1 equals mu2. Either are fine. They're both perfectly acceptable. Yay. Okay, I'm great with that. How about an alternative hypothesis? You want to read the question to be able to figure out what the alternative should say. And here it says, is there evidence that the average pulse rate for smokers is higher? So what are we looking at here in terms of our null and our alternative? That's perfectly one way, great for one way to say it. Could also say that the difference is greater than 0. Okay? Either one is perfectly okay. Any questions so far? All right. Then we're going to go ahead and move to our plan. Okay? So far, the only difference is our notation is in terms of the parameter mu, and we're doing the different name of a test. But everything else is kind of the same so far. Do you agree? When we get to our plan part, that is our checking of our assumptions. Would you agree? Or our conditions is the word I tend to use more often. And there are always 3 of them. And they are different with means. We're still talking about the independent, normal, and random. So there's the names are still the same, but what we do to check them are a little bit different when we talk about means. I feel like I'm a broken record at this point talking about this, right? So what do you want to do first? Random? Sure. Look at random. What does it say in the problem? Is this an experiment? You're not putting someone in a room and saying, smoke, do it, right? You're not imposing a treatment on somebody, are you? No, okay? So this is not a random experiment. It's going to be just a random sample. Would you agree? Now read what it says. Does it say that they were randomly chosen? Yeah. So you can just say at one time if you want. You can say that both samples were collected randomly. I would accept that. All right. What's the next condition? The normal condition, if you want to check the normal condition, we have to have sample sizes greater than 30. Different than it was for proportions. Remember, for proportions, it was NP is greater than 10, or NP hat, right? Because we had to use the P hat with the two proportions. But that's not true here. Both of the samples aren't greater than 30. One of them is. But what does it say in the problem to help us? It's, yeah. So because of that sentence, that satisfies the normal condition. So we just need to say that, okay? So we're going to say that both sets, we'll say both sets of, I'm just going to repeat the sentence. Both sets of data are relatively symmetric with no outliers. Therefore, what just happened? Therefore, normal condition is met. Normal assumption, normal condition, however you want to think about it. Okay? What's the third condition? The independence condition, which is our 10% condition. And we want to look at our two sample sizes, and we want to think about, is 32 less than 10% of all? I think it's the 32 goes with the non-smokers, right? So, yeah. Would you agree with that? So you would just say 32 is less than 10% of all non-smokers. And then the other sample size was, thank you, 26. So 26 is less than 10% of all smokers. So our conditions have been met. Our assumptions have been met. Therefore, it is safe to continue with our two sample t-test. So what's the next step? We got to do it. Okay? So when we look at doing it in terms of performing the test, we need to do a test statistic and a p-value, and this is where you're going to be doing that information. Let's start with our test statistic. It is a t. Now we got to think about what we're going to be doing here. The formula for any test statistic is the statistic minus a parameter over the standard deviation. So look at your formula sheet and think about what is going to be different here. Well, maybe we should come up here and pull out some of the numbers and list some things that are important to us so we know where they go in the formula. Will that make sense? So let's go ahead and look at that. So in other words, I'm just going to put it up in the state part. It doesn't really matter where. But I'm going to say, well, I know I have a sample mean. I know I have a sample standard deviation. And I know I have a sample size, all from the smoker population, because I'm deeming that population 1. Is that okay? And I'm going to have that same information for the second sample, which is our non-smokers. Okay? Those are important pieces of information because those are numbers we're going to put into our calculator eventually. And they're also numbers that we're going to put into our formulas. So when you read our problem, what is the mean for sample 1? 80, okay? We have 80 beats per minute if you're a smoker. And then the standard deviation would be 5. And our sample size was 26. And if you look at the second population of non-smokers, we're deeming that population 2. We have 74 as our mean, 6, and 32. Okay. So just kind of pulling out the numbers for each of the two different populations, kind of thinking about where those numbers need to go. And then we'll come down here and we'll plug them in. All right. So what numbers go in the top, in the numerator? Well, you're going to subtract looking at the difference, right? So it's the difference of the two. And then aren't we also subtracting 0? Isn't the parameter, the claim, the difference going to be 0? Isn't that what we're testing against? So we're going to eventually subtract 0. Some people tend to not write that minus 0 there, and that's okay. All right? I'm just going to go ahead and put it because we're used to saying statistic minus parameter. Okay? So that's just why I'm putting the minus 0, but it's not required. What numbers go in the parentheses? Yeah, so it's the two different means. Should I write the formula first and then put the numbers in? Okay, no problem, I can do that. So it's going to be x bar 1 minus x bar 2 minus 0 over, and then so that's going to be 80 minus 74 minus 0. And then the standard deviation It's actually standard error because we don't have population standard deviations, right? We have to use our sample standard deviations. And so it should be the first standard deviation squared over its sample size plus the second one squared over its respective sample size and the square root of all of that. Double check your formula sheet. The formula sheet tends to write them a little bit differently. I'm not sure if it writes it exactly like this. A little bit. It just uses a different letter. That's okay. All right, so we're just going to plug in the numbers. So I got, what, 5 squared over 26 plus 6 squared over 32. And I'm going to pause the recording because I think it's valuable to go ahead and try to find this on the calculator. Go ahead and try to simplify that and tell me what your test statistic actually is. So yeah, you get 4.154 is what I got. It depends on how you round it. I tend to round to 3 decimal places. Close, hopefully. All right. Now what? What was the p-value? Okay. When we think about drawing this, when we're talking about t's, what goes in the middle? 0. Good. And so we have 0 here, and we're going to put 4.154. And since our alternative hypothesis was greater than, aren't we shading to the right? Yes. Okay. All right, how do I find that value? TCDF. Okay. And we're going to say 4.154 to the right. But I'm going to pause. What number goes there? That's the degree of freedom. Good. What is it here? Okay, so remember how I talked a little bit last class, it's been a while, but you really have 2 choices here. You can either be safe and use the smallest sample size minus 1, which in this case would be 25. Okay, that's perfectly okay. If you want to use a degree of freedom of 25, go for it. But what does a calculator do? It uses some crazy formula, right, that I'm never going to ask you to do, but it is appropriate to use what the calculator gives you, okay? So you may either, all I ask is that you tell me which degree of freedom you're going to use, okay? So in my case, if you want to say degree of freedom equals 25, because it's 1 less than the smallest sample size, that's perfectly okay. The only thing I would warn you about is that if you use that number, your numbers won't match the calculator. Okay, and just know that. I think that happened to us last time, didn't it? When we did the confidence interval. Perfectly okay, perfectly acceptable. The work will not be wrong. It'll be accepted. It's perfect. It's fine. I tend to, because I am like OCD, I need everything to match up and be right. Like I want it to tell me what the calculator tells me. So I'm going to just use the degree of freedom the calculator gives me. It happens to be 55 point something. I'll tell you how to find that in a minute, okay? It is 55.95. So I'm just going to tell you that that is the degree of freedom, and I'm going to tell you that that's what the calculator gave me, okay? If you're going to use the calculator degree of freedom, you need to tell me that, or tell AP that. Fair enough? Otherwise, just use 25. Okay? All right, so I'm going to use 55.95. Again, I will show you how to find that. And then go ahead and tell me what that p-value is. Do we expect it to be small? Yeah, because isn't that an unusual test statistic? It's pretty high, right? Tell me what you get. The number I'm going to write down is going to look different than what your calculator gives you, but make sure you understand that they mean the same thing. When you look at what the calculator output is for the p-value, when you enter this in, you're going to get 5.6 times 10 to the negative, or I think the calculator notation is 5.6e negative 5, right? That just means times 10 to the negative 5th power. That just means you're moving the decimal place. What what AP doesn't want you to do is write that E notation. They're really anti that for whatever reason.
Could you go 10 to that?
That would be okay, but just don't, the E thing, I don't, for whatever reason, it bothers people. I'm just relaying information, okay? So I would just tend to just move the decimal place and tell me what it is. All right, so the P is low, we're gonna reject that ho, right? Okay, so let's go ahead and conclude. We got a really low P value. It doesn't say what to compare it to, so we will just tend to say that our alpha is 0.05. Unless it said it, I don't think it did here. So we're going to reject the null. And what are we going to say? What's our context conclusion? We either have evidence to suggest something or we don't have evidence to suggest something. What do we have here? We have evidence. Not only do we have evidence, you can even use the word strong here. Why? The p-value is so small. It's so unlikely that our sample happened assuming that that null is true, right? It's really not, it's not going to happen. So we have strong evidence to suggest. To suggest what? Look back at our claim, look back at our state. What are we thinking of? What did the question ask? Always go back to the sentence stem. Yeah, I would actually, that's a good thing to practice doing. When you're writing your context conclusion, go back to this last sentence and write your answer in terms of that, okay? That'll help you. So what we would say is we have strong evidence that the average pulse rate for smokers is higher than that of non-smokers. Now, if you look at the next question, it's asking you how much higher. But before we get to that question, are there any questions on this? I thought this was kind of nice because you didn't have to worry about the graphs because it already told you that they were fine, right? The normal condition was met. How do we feel, okay? Any questions? I know y'all have had 3 days off, but come back to me. Good? All right. We'll look at the next question. So, how much higher? What am I going to have to do to answer it? Well, it tells us to construct a confidence interval, right? It may or may not give you that second part. It might just say how much higher. So you really kind of need to know that when that question's being asked, that means confidence interval, okay? So, what's the formula for that here with two different means? We did this before, didn't we? Didn't we do this last class? We should have. There's your formula, right? Go ahead and do it. I'll pause. Degree of freedom with the calculator. Let's do that real quick, especially since we've already done one of these. Let me go ahead and pull up my calculator and just turn the lights out so you guys can see it. So if I'm going to go ahead and look at the 2-sample t-test, which is option 4, notice we've done quite a few of these tests so far. Okay? So 2-sample t-test. We're going to go to the statistics because we're not entering lists of data into our calculator. That's actually what you'll do on the back, okay, as practice. And we'll just type in. So our first sample mean was 80. Our standard deviation was 5. The sample size was 26. And we'll just put the same information in for our second sample, which is our non-smokers. Now, we have to also tell it which one it is greater than. What are we going to do for pooling here? Don't do it, ever, for means. Only for 2 proportions. And this is the degree of freedom. It gives it to you, 55.95. All right? So that's where I got the number from. Is that okay, Bryce? Okay. So the calculator uses that complicated formula to give you, I mean, the higher degree of freedom you use, the better. So you want to use a more accurate one if you can. But again, to play it safe, it's the smallest sample size -1. It's never pooled for means. All right. Thank you for, and we should have everything else match up. Our test statistic looks like it's the same. The p-value looks like it's the same. So we did okay. Awesome. All right. Any questions so far? Thank you for bringing that up. Yeah, sure. So on the calculator, or it's a two proportion t interval. I'm sorry, not two proportion. A 2-sample t interval. Oh, I'm sorry. You mean percentage? Right? Well, how confident do we want to be? If it doesn't say, 95 is going to be our default. Yeah, I'm sorry. I didn't understand your question. Yeah, so we'll go ahead and do a 95%. Since it didn't say, especially since we use an alpha of 0.05 above. You kind of want those to match, okay? Not you kind of, you do. I think I said 2 decimal places what I did. I said 55.95. I'm very hesitant to ever round to 1 decimal place, to the 10th place, ever. Go ahead and tell me what numbers you get in here. Tell me if you get the same thing I do. Hopefully, this is what you got. Okay? Perfectly okay. Perfectly okay. I think the calculator does too. If you do a 2-sample t interval on the calculator, I think it does go out to 4 decimal places as well. Are we okay with how we did the inverse t, how we got our t star? I again used 55.95 as my degree of freedom. You could have used 25 and been okay. You would have gotten a different t star, but as long as you showed your process, perfectly okay. But since I want them to match up, I'm going to use the one that, yeah.
So if you said we have to write which degree of freedom is doing either the calculator or the smallest one, how do you
So I literally, like on the other problem, I just wrote degree of freedom on calculator. Like I wrote degree of freedom on calc. Okay? Or you can just say degree of freedom and then give me 25. And you could say smallest sample size -1. That part's not necessary. The on calc part would be necessary. Good question. How do I interpret this? Remember what we're dealing with. We're dealing with the difference between smokers and non-smokers, right? So what are we actually confident about? We're 95% confident that this interval captures the true difference. Do you agree?